Today is 2026, 7th of January. I'm with MIT's Professor Seth, and this is Sunghyun. Nice to see you.
Nice to be with you, Sonia.
I was really impressed with his fashion and lecture quality, and I'm going to have questions related personal questions and quantum computing questions and science general questions. First question is, I was really interested with your background. You studied philosophy and you also majored physics. And during the class, you kind of showed us a lot of good philosophical words and also Emily Dixon, such as uh, literature related words you also use it in physics. Uh, do you think what is your advantage, practical advantage you after you majored philosophy at UK? Do you really apply such things while you are studying or researching?
Oh, yeah. So I was an undergraduate. I did my undergraduate degree in physics at Harvard, and then I got a very generous scholarship, a Marshall Scholarship from the British government to go study at Cambridge for 2 years. The first year I did Part 3 maths, which was a master's degree basically in math and physics, quantum field theory, and gravity. And then the second year I didn't know what to do, and because I'd never always been mystified by quantum mechanics, I decided I would do MPhil in history and philosophy of science, looking at quantum mechanics and ideas of information theory, because I'd also always been interested in information theory. There wasn't really a field called quantum information at that point. It
No.
didn't really get called quantum information until the 1990s, until 10 years later. And uh, that was it was very fun. My supervisor, Jeremy Butterfield, allowed me to apply these ideas of information theory to quantum mechanics, and it was very fruitful. I still, at the end, I was still mystified by quantum mechanics, but at least I'd studied all these ideas in philosophy. And moreover, I think it's been very, very helpful for me because I actually know how philosophers think about physics, like actual philosophers of physics, and how philosophy of physics is rather different from what many physicists think. Many physicists regard themselves as philosophers, um, which is okay, but it's actually the motivations of philosophy are often rather different from what physicists think they are. And so at least I know that, and that's very helpful. That's been very helpful. And I feel a lot of physicists, when they talk about philosophy, get themselves all tied up in knots, which if they were thinking a little more clearly, they wouldn't have to do. The other thing that was great about it is because I've been studying, a lot of quantum field theory and also classical gravity. Classical, I've taken classical general relativity 3 times by then. I took Stephen Hawking's graduate seminar in quantum gravity, which was very important to me. And in fact, then that inspired me to try to embark on what's been a kind of lifelong project, which is to try to see if you could come up with a theory of quantum gravity, which is something nobody has, even though people who are doing ADS CFT right now claim that they have a theory of quantum gravity, but it's not very satisfactory in many respects. For one thing, we live in de Sitter space, not anti-de Sitter space. And studying quantum gravity with Stephen Hawking was very inspiring. And I decided to see if I couldn't come up with a way of understanding quantum gravity in terms of quantum information, which has been very fruitful. In fact, quite ironically, now it's 40 years later, and now finally, finally over the last maybe 5 years or so, now the idea of relating quantum gravity to quantum information has become very trendy, including amongst the quantum gravity people. So that's kind of entertaining for me.
If I have follow-up questions, do you have any famous quote or sentence in philosophy, and also famous quote or maybe equation in case in physics or mathematics? And maybe do you have any relation that you connect in between?
Oh, oh, that's a funny question. Uh, 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 famous quotes from philosophy. Um, Well, one of my favorite is, of course, the way that Wittgenstein ends the philosophical investigations, where he says that of what we cannot speak, we must perforce remain silent. And I think many physicists would do well to remember this quote.
Mm.
They often seem to say things when they'd be better off being silent. And famous equations in physics, well, I don't know. I mean, they're all good, they're all good. It's just a question of which are the ones that are really useful according to what problems you want to solve at that point, at that moment.
And during the class, I was actually very impressed with your dancing skills and also your example with hand and rotating it to show 4 pi I. Like, how did you get such good body skills? Like, usually people in academia don't have such dynamic skills. But I think you have dynamic skills.
Like, like you practice singlet dance like enough times and like then you get good at it. It's like a question of practice. I actually, yeah, the I've done a lot of work on quantum biology starting in 2008. Alana Asperbuzik and I started applying the methods that we had developed for looking at open quantum systems for quantum computation to excitonic transport and photosynthesis, which is kind of, our theory, and this is, I think, widely agreed, is that excitonic transport, a photon comes in, it's absorbed by a chromophore, creating an exciton, a bound electron hole pair, which is kind of like a particle of energy. And this energy hops from chromophore to chromophore, like chlorophyll molecule to chlorophyll molecule, until it gets to the reaction center where it's charge separation takes place and it's turned into chemical energy. And I developed our theory turned out that there's a really, you can describe it using an interpretive modern dance. The interpretive modern dance is entitled The Interplay Between Decoherence and Anderson Localization and Excitonic Energy Transport. And it's very effective at conveying what happens. And so actually, so when people would ask me to talk about this, like give a physics colloquium, I would do this dance, and once you see the dance, you understand what's going on. And then for many years after that, people would invite me to give a colloquium, and I was working on lots of other stuff. And I'd say, well, what would you like me to talk about? I could talk about this or this or this. And they say, we want the one with the interpretive modern dance about energy transport and photosynthesis. So I would have to do that. Yeah. And this demonstration of the fact that if you have something that's attached at a distance to something which is fixed and actually cannot rotate or all the way around, the fact that you have to go around by not just by 2 pi, but by 4 pi is something I learned, I think, from Sidney Coleman, actually, from whom I took quantum field theory. He was a famous quantum field theorist and an amazing teacher. His classes he was very funny and he was very compelling. And every class you'd leave thinking that you really understood what was going on. And then you'd try to do the problem set and you realize you didn't understand anything.
Thank you for answering. It's very valuable answer.
I think there was also an experiment with a belt also, right? With the twist when it's like held. I mean, similar to the 4 pi rotation.
Oh, I don't know about that one. I got to learn that one.
Oh, sorry.
And also fashion sense, I think I thought you had a very good fashion sense that had black jacket and hat. Is it also from when you are studying philosophy, or it's separate?
Well, it had not occurred to me that I have a good fashion sense. I had not thought of that, but I'm glad that I do. Anyway, no, the dressing in black is something that I started doing when I was a graduate student living in New York City in the 1980s. And it was a very dirty and dangerous place. And if you dressed in white, when you came home in the evening, you'd be covered with dirt. And so dressing in black was the wise thing to do. And everybody dressed in black. And that's just the way it was. And, I lived on the Lower East Side. I had a bunch of friends who were artists, and they all dress that way also. Actually, I mean, but I don't know if it's trendy or not. Anyway, my children get very annoyed. They said, "Oh, Dad, you're dressed all in black again." I said, "Oh, am I? Oh, yeah, you're right."
And I want to also ask you the framework when you see the life or specific problem set. Like I think everyone has framework, like maybe some specific object or notion, and they usually see the word. Like, do you have any specific your own framework? How you approach to the framework or
Oh, so when you say about approaching, you're not looking at talking about quantum biology, you're talking in general.
in general?
Yeah, well, I've always liked ideas of information and computation ever since I was a kid. Uh, I started learning binary numbers and about computation when I was something like 10 years old. When I was 9 and 10, I got really interested in binary numbers, and I had a teacher in my local elementary school who knew all about that kind of stuff. She was very helpful and learning about ideas of computation. I had from Edmund Scientific, I had a little mechanical computer that was like, you programmed it by it was made out of plastic. You put these little plastic pegs in different places, and then there was a clock that you moved by hand, and then it would update the computation and mechanically perform digital computation. I thought that was really fascinating. And so I was very interested in ideas of computation starting from quite a young age. And point of fact, the quantum computers that, as you know, I made the first proposal for how you could build a quantum computer using, integrating both quantum logic gates and, moving information around in the quantum computer and then performing universal quantum computation back in 1993. And then I worked with a bunch of experimentalists to implement quantum computers on a whole bunch of different substrates, starting with nuclear magnetic resonance and then atom optical systems. I worked with Hans Moyen and Terry Orlando and Caspar van der Waal to build what ended up being the second superconducting qubit in 2000. And so these simple quantum computers were a lot like, these simple computers that, I had when mechanical computer that had, like 8 3-bit words or 3 8-bit words. And that was so that was fit in very well with that. And then I've also just like the idea of information in the abstract. And so in my PhD, though it was in a high energy physics department, I started working closely on ideas about physics of computation, reversible computation. The very first ideas about quantum computing were coming out at that time. And so I followed them. I mean, there were very few people working on this topic and very few people were actually interested in it. And so luckily I met all and worked with all the people who were doing that, people like Rolf Landauer and Charlie Bennett, and then people like Bill Ruders and Wojtek Zurek in particular was a very important person to work with about quantum mechanics and open systems and decoherence. Then Murray Gell-Mann, with whom I did my first postdoc. And by then I was working on ideas of applying information and computation more broadly to understand the world, to understand what it means for a system to be complex and how we can characterize complexity and what are the different types of ways that things can be complex and whether, being complex may allow you to solve more problems than you could otherwise, but it also might make you more fragile to different kinds of perturbations. So I really, you could say that my work in general is informed by the role of information in the universe and the role of information and computation in the universe. And that's my kind of prejudice when it comes to looking at the universe. I wrote this whole book, Programming the Universe, which basically says, okay, and this came out of trying to build quantum computers. When in figuring out all these different methods for building quantum computers, the central insight is that all physical systems, quantized systems, carry information. They're discrete. Any 2-level quantum system, like an atom in its ground or excited state, or a nuclear spin, or electron spin, or a photon that can be polarized like that or that, these are quantum bits. And then if you can arrange interaction between those bits, then you can learn how to speak the language of that particular, say, atom optical quantum system. You tickle it in the right way, massage it in the right way. You can convince it to perform computation. And so then this realization of trying to build quantum computers, I realized, oh, well, everything actually is already computing and processing information at the quantum mechanical level. And if we want to build quantum computers, we simply have to kind of hack into this computation. And so then programming the universe, the thesis is the universe is a giant quantum computer, and let's figure out what the implications of that are. And it's not even, this is not a metaphor, it's actually the case. The universe is quantum mechanical. It stores information in digital quantum mechanical form. It processes that information via interactions. These interactions are computationally universal because they support universal computation as in the computer that we're recording this on. So it's not a metaphor, it's a fact that the universe is a giant quantum computer. And then what are the implications of that? They're pretty wild.
This could be a bit philosophical. If you, as you said, the universe is giant computer, then what will be the end of the result of computation at the end? Or is there any implication that you are, from a lot of implications, there can be a lot of implication. Is there any implication that you are very interested in? If you just choose one or two.
Yeah, well, I mean, I believe strongly, and that's certainly, in my career, I put my money where my mouth is, right? That it's, if you study how the universe processes and registers and processes information, that you can understand all kinds of things about the universe, which you aren't able to understand otherwise. I mean, a good example of this is the laws of physics, which are quantum mechanical in nature, are very simple. You can, I see them at MIT written on the back of a T-shirt, right? And the initial state of the universe appears to be very simple. And so you have simple laws and the simple initial conditions, and yet these evolve into tremendously complicated structures in the universe. Why does that happen, right? That's a real mystery. But if you think of what's going on in the universe in terms of computation, then it makes sense, because in a computer, you can have a very short program that will cause the computer to create structures of arbitrarily large complexity. An example of this is just, you can write a very short program for a computer that says, evaluate the outputs of all possible computer programs, right? Suppose the first bit of the program is 0. See what happens. Is that an instruction that says to do something, or does it say look at the next bit, right? And then you can say, okay, and then look what happens if the first bit is 1. Does that say to do something, or it says to look at the next bit? Okay, let's suppose it says look at the next bit. Okay, so now we look at if the first bits of the program are 0, 0, or 0, 1, or 1, 0, 1, 1. And this is a very simple program. It evaluates either sequentially or in parallel, if you have a parallel processing, all possible programs. And some of these programs create structures of very high complexity. So you have a very simple program that provably, by whatever definition of complexity you like, will create structures of arbitrarily large complexity. And that's what we see in the universe around us. And I think this is a very good explanation for why the universe is complex, which otherwise we don't have. I don't know of a better explanation than that.
Complexity and structure.
Yeah, why the universe generates complex structures, which is a very mysterious thing if you just look at physics in and of itself.
Now, I want to ask you questions related with your young age. What are your dreams when you were young? And also, I want to ask you, what are your dreams currently? And yeah, these two things.
Yeah. Well, I was a very dreamy kind of kid because I was always thinking about different kinds of things, and I really liked mathematics, and I very rapidly, really starting, at a very early age, like 6 or 7, they would give me stuff to solve and I'd solve it. And then the teachers didn't have time to help me with other stuff, but they'd make some suggestion, maybe you look at this. And so then I would teach myself some other math and, then some more math and explore that, which I really enjoyed doing. And then when I first started studying physics maybe in junior high school, I thought, wow, this is really amazing. This is another amazing thing about the universe, is that it actually is described by these simple mathematical laws, and that's really remarkable. and and mystifying, right? I think that was Wigner may have called this the unreasonable effectiveness of mathematics, is the quote. And uh, that is always fascinating to me. And so I was a dreamer. I was a very dreamy kid, and I was dreaming about, different aspects of mathematics and physics and the way things were put together. And I'm still a very dreamy, now older adult, doing exactly the same thing. So at least I'm consistent. I don't, my dreams were not, I did not dream about, oh, I'm going to change the universe in this way, I'm going to do this or that, or I'm going to like solve this problem or that problem. I just, instead I just tried to solve problems. I thought my time was better used trying to solve the problems rather than dreaming up, oh yeah, well, but also dreaming up new problems,
Dreaming up new
right? Yeah,
problems.
so that's a very difficult thing, right? Uh, uh, and when you go to graduate school, right, you're you're you and all through school they give you problems to solve, and you get really good at giving problems, at solving problems that people give you to solve. But the real hard problem in science of any sort is figuring out what the important problems actually are and being able to formulate a new problem in a way that it could be solved, right? So it might actually be solvable. And that's extremely difficult. And weirdly, nobody teaches you how to do that.
Yeah.
They just teach you to solve problems that they already have. So yeah, that's I think the most important skill for doing new kinds of research. And for that, the main thing I think is just to be playful,
Playful.
playful, just fool around with things, say, oh, let's put these two apparently, completely different ideas together and see if we can't find ways in which we can relate them in some kind of rigorous fashion. And so then if you try out a bunch of different, and it should be something that you find interesting and fun, and then just trying out there some things that might seem crazy, and then it turns out that indeed most of them are crazy, but every now and then one of them seems to work. So that's, I think, a very important, that's an important part of life for anybody, not just in science. I think that people are insufficiently playful. And then, of course, in physics and mathematics, then you can be playful, but then at some point you've got to buckle down and make it rigorous. So trying to come up with, be playful and try to generate some new idea and then being able to solve it, that's a great thing if you can do it. And that's certainly a beautiful way to spend one's time, even if most of the time it doesn't work.
If I ask you just in very detail, then play with new ideas. And if you think some new good problems, if you think you just discovered it, then you're kind of checking complexity, or how do you when is the point that you actually make it rigorously? When if you look, you will probably make it rigorous when it looks valuable. Yeah.
Well, I mean, I don't know, like let's say, so okay, so I was so in the 1980s, so Paul Benioff proposed the notion of a quantum computer in 1980. And this was a very abstract notion. And David Deutsch proposed the notion of universal quantum computation in 1985. And but all these proposals were very, very far from any kind of physical reality. And so when I was a postdoc at Caltech, working with Murray Gell-Mann, starting in 1988, I decided I would see maybe how you could build a quantum computer, because nobody had apparently asked that question before. And then, so I talked with a lot of experimentalists and people and theorists who were working on different kinds of physical systems. And then, in particular, systems that involve systems like atoms or spins interacting with quantized electromagnetic modes of light. as in, for example, the James Cumming model. And I never took any courses in those kinds of things. I just taught myself what I needed and talked with people. And then finally, after about, I don't know, I think I started really trying hard in around 1990 with this, and I had a lot of false starts. But then by 1992 or 93, I'd learned enough, so I realized that if you had, say, interacting spins or atoms or quantum dots, and you address them using electromagnetic resonance, you could, well, of course, you can perform single qubit rotations.
Right.
That's, of course, very well known. And then the other ingredient that you need is a reversible universal logic gate, like a Toffoli gate or controlled NOT. And I realized that if you have three spins and they were just interacting with each other, pretty much any interaction, then you could, and you tickled them with light of the right frequency, then you could flip the third spin if and only if the first two spins, say, were spin up, which is a Toffoli gate. So that gives you a universal gate. And then, of course, the other tricky thing is if you have many of your qubits, you have to move information around from one place to another. And so I figured out how, again, using electromagnetic resonance in regular arrays of atoms or spins or quantum dots, how just addressing them all in parallel, you can take a quantum bit that was over here and move that quantum bit over to some other place and then have it interact with another quantum bit that's coming from the other direction to form a quantum logic gate. And with those three elements, single qubit rotations, well, that was known. Performing a Toffoli gate, that was not known. But then using this very basic, electromagnetic resonance, just like straightforward interactions of atoms or spins with lasers or microwaves, and then the kind of sneaky tricks for how you could move information around in arrays of atoms, that's enough, because then you have a universal set of quantum logic gates. You can construct any wiring diagram you want, and that gives you a universal quantum computer. That, finally, by 1993, I'd figured it out and wrote this paper called A Potentially Realizable Quantum Computer. That was very, it was a big effort. It took a long time. It took many years. So admitting, but that's a reasonable thing. It's like, okay, people talk about quantum computing. It's like a nice idea. We didn't have any good algorithms. Like, we had just a Deutsch-Jose algorithm, which is, it's nice, but it's not very impressive. It's not useful, particularly in any particular sense of the word. But I figured, okay, let's see if we could build something like that. And indeed you could. And that was actually kind of lucky because for me, because I had a terrible time getting a job because nobody was interested in quantum information. And, when I was a graduate student, I applied for 92 postdocs and I was turned down by 90 of them until finally Rolf Landauer offered me a job, and then Murray Gell-Mann offered me a job. And then 3 years later, I was applying for postdocs again, and I couldn't get a postdoc. I only got one postdoctoral offer from Don Farmer at Los Alamos. And then the next 3 years, I was applying for all these faculty positions, and I didn't get interviewed for any jobs in a physics department. So, and I was very lucky that I applied for this job in mechanical engineering at MIT, where turned out the mechanical engineers thought that the idea of building a quantum computer was pretty cool. I would also done all this work on complex systems, and they liked that. So they actually offered me a job, which was amazing. I mean, could easily have ended up driving a taxi cab. And yeah, so that was lucky. And then that was really lucky because in 1994, I got to MIT in 1994. And in 1994, Peter Shor came up with Shor's algorithm, and I already knew how to build a quantum computer and had started working with people with a whole variety of different technologies to realize quantum computers. And so we very happily, started building quantum computers. Ike Chuang and Lieben van der Sijpen and Debbie Lungen did the first quantum computation, Deutsch-Jose algorithm using NMR. Worked with Dave Corey, Franco Wong and Jeff Shapiro on quantum communication and quantum metrology. And then, we're at the same time, I and colleagues were coming up with algorithms. I came up with the fundamental algorithm for doing quantum simulation. And Lorenzo Maccone and Vittorio Giovanetti and I worked out the basic quantum limits to metrology, the notion of, showing that Heisenberg limited metrology was the best you could do. And then here's how you do it. So, and that was extremely fun. And these were all things that you know, th- they were kind of out there, these questions, but there were very few people working on them. And so I was also sort of lucky that when nobody's working on a question, then it turns out that there may be questions that are actually not that hard to solve, and they've only not been solved because nobody actually thought of working on them before. So yeah, that was very fun, and that continues to happen, right? So I think it's like, like for instance, in the last 10 years, Patrick Reventros, my postdoc, came to my office in like 2012 and said, "Hey, Seth, let's work on quantum machine learning." And I said, "Great, what's machine learning?" Right? And he started to explain, these basic machine learning techniques. And I said, I see. Okay, well, this we can do, right? So then we started developing these algorithms for machine learning back in 2008. A friend of mine, Ricardo Zucchina, came to mind and said, Seth, why are you guys always trying to get these exponential speedups with Shor's algorithm? Why don't, if you could even if to invert an n by n matrix takes time n cubed, if you could even get it down to like n squared, that would be great. And I said, well, that's a good idea. It's an interesting idea. And so I thought about it for a bit and came up with the basic idea, the engine that powers our linear systems algorithm with Aram Haro and Avinat Hasidim, where it turned out indeed you could invert an n by n sparse matrix in time, as it turned out log n. And actually, yeah, and then invert, if it's not sparse, you can indeed get it down from, n cubed to order n or n squared. So yeah, so that was like, nobody had actually ever thought of trying to do that, even though in retrospect it was an obvious thing to do, because actually it seemed bizarre that you could invert an n by n matrix in time log n, but probably why nobody thought of doing it, because it sounded impossible. But actually it turned out to be okay.
No.
Yeah, so then in the quantum machine learning, I mean, 2011, 2012, that was just when actually deep neural networks were starting to work well. So machine learning was just starting to become effective and popular at that point, and nobody really had thought of trying to do the quantum version. But it turned out that a lot of the very basic techniques for particularly things like, traditional methods like kernel methods, like support vector machines, they're all linear algebra based, and then that means that you can solve them. And what more recently? Oh yeah, then like about maybe 6 or 7 years ago, another friend, Mario Rossetti, said, "Oh, why don't you look at this problem of topological data analysis, which is the problem, you have a very high dimensional data set, or even just you say a discretized manifold, like a simplicial complex, and you want to find the number of connected components and holes and voids of different sizes. It's called the homology, simplicial homology or singular homology, very basic procedure in algebraic topology. And I didn't know any algebraic topology, so Paolo Zanardi, who knew more algebraic topology than I did, we sat down and we started thinking about it, and then I said, oh, like actually this algebraic topology is all about actually, in this case, you want to project onto the kernel of a very large, a 2 to the n by 2 to the n sparse permission matrix, the Hodge Laplacian, and or a simplicial Laplacian. And actually I knew how to use the quantum phase estimation to project onto the kernel of a very large 2 to the n by 2 to the n sparse matrix. So then the question was, okay, fine. So then we got these exponential speedups for doing homology and cohomology, which is an extremely basic fundamental procedure in algebraic topology. So that meant, we'd actually, just nobody thought of doing that before. So that's fine. So yeah, so it was good. And that was that was pretty cool, because as a kid I'd always wanted to thought I would be a mathematician. Then when I got to Harvard, and I took Math 55, which is the famously difficult freshman course for people who want to be mathematicians, I realized, whoa, this is tough. And it didn't help that my class had 3 out of the 5 members of the US Math Olympiad team. So there were definitely people there who were smarter than I was at math. And at the same time, I was taking physics, and I realized, oh, actually, I'm really liking this applying math to physics. But it was very nice, like many decades later, to actually realize, oh, actually I could understand some of these things about pure math and even make a contribution to pure mathematics via quantum computation by coming up with quantum algorithms for doing pure mathematics. That was cool. What goes around comes around, they say.
Thanks for like your whole journey. I think I can really feel in touch like how you approach to the problem. And if I ask you the question, I think if I see professors in my like around, they usually define the problem. I think quantum computing for you and in the world, I think it's huge problem. But if you can define quantum computing as a problem, can you define it in one sentence?
Yes, so, well, now, right, I think that's a little unfair when I said that the real problem is formulating the problem, right? So I guess maybe I would say, look, a, a very straightforward and fundamental way of looking at the world, which is correct, is that at bottom, the universe is processing information, at the level of elementary particles, at the level of molecules, at the level of, neurons in the brain. So the universe is out there processing information. What are the implications of that? And how does this help us understand what's going on? And in fact, there are many implications. And at least it's helped me understand better what's going on. And I think it helps a lot of people understand better what's going on in the universe.
Thanks for your definition. And lastly, we are almost at the end of the interview. I think I will ask you two things. My channel started by interviewees later want to see their channel again and like time capture, they can remember that. Maybe is there anything you want to say in here to remember for your future yourself? Did I remember?
To the future Seth,
Future self.
when you're dead, don't remember. I think I can promise to do that.
Okay. And thanks for the interview. And really, lastly, is there anyone you want to listen others' opinion, or yeah, it is basically it was basically used for me to find my next interviews. So if there's anyone you want to interview, yeah, this will be my final question.
Oh, well, I interview enough people. I for my job, I don't want to interview anybody else. Yeah, I don't know. I personally like talking with pretty much anybody who has a novel and fresh perspective. So yeah, I'm afraid I don't have any
It doesn't
specific recommendations.
It doesn't need to be scientists, but it can be just totally different area, like such as who write a novel, or yeah, a singer, or anyone else.
My daughter Zoe is an excellent singer. Zoe Lloyd, available on Spotify. Her recent album Roadside Attractions. You'll love it.
Okay, then today, thank you for your interview, and we'll see each other next time.
Okay, thank you very much, Sonia.
Thank you.